Okay, so if you're watching this, I assume that you already know that we have number of digits, and um, number of options, like successful options that don't have 1 next to each other. So if we have 1 digit, there's 2 options, either a 0 or 1. 2 digits, there's 3 options. Um, These aren't obvious without listing them out, but I'm assuming you've done this already. So you continue this pattern out to 12, and you get your answer there. The question is, why does this pattern hold up? So if you're trying to use Fibonacci or you're trying to use induction, those aren't Fibonacci itself. You can't just say it fits Fibonacci. Fibonacci means that each one is the sum of the previous two. And if you use induction, when you get on the inductive step, you're going to have to show that the next one is the sum of the previous two. So either way, you need to go to the actual pattern. So let's think about all the different combinations for 3. So for example, we have 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, and we would have 0, 0, 0. So these would be the different combinations for 3. What about the combinations for 4? Maybe a slightly different color here. Let me also list them out a little more systematically. 0, 0, 0, 0, 1, 0, 1, 0. I'm kind of going by binary here. 1, 0, 1, 1, 0, 1, and 1, 0, 1, 0. Okay, so these are the 5 that have 3 digits. These are the 8 that have 4 digits. Now the question is, how many have 5 digits, or how do we get the 13? So what I would suggest you doing is trying to figure out how can you get the 13 solutions with 5 digits from these 13 codes. And specifically, I'm going to suggest that you think, what could you add here to transform these into 5-digit ones? And what could you add here to transform the 3-digit ones into 5-digit ones? Because that would, if we could figure out why all the 5-digit ones are coming from the 3-digit ones and the 4-digit ones, and that gives us all the 5-digit ones, then that pattern holds for higher numbers too. So the question you need to figure out is, what could you add here? So here you're going to add 2 digits, right? And here you're going to add 1 digit. And what pattern could happen? So then if you did 4 and 5 and you added these 2 digits to all the 4s and this 1 digit to all the 5s, you would get the 6s and so on. So when you're counting the number of options, there's 2 things you have to be aware of. And then this will complete your proof. 1, make sure you have no duplicates. Whatever you add here, make sure you're not getting any duplicates. For example, if I added 0, 1 here, and I added a 1 right here, if I would add right there, if I would add 0, 1 here, and I would add 1, this is the same. 0, 0, 1, 0, 1 is the same as 0, 0, 1, 0, 1. So this would be a duplicate, and suddenly I would not have 13 unique solutions. So I need to make sure I don't have any duplicates. I also make sure I have all possibilities. So how do I know there's not more than this 13? Can you come up with an argument that there's not more than the 13 that we have using the method you've done to put these 2 digits here and the 1 digit here? And one final hint, the 2 digits you put up here at the top will be the same for all 5 of them, and the 1 digit you put here will be the same for all 8 of these. See if that gives you something to work with.